So the question is quite straightforward. We are told that the voltage across the terminals of a 0.5 microfarad capacitor is 0 at t less than 0. That is before we start doing any calculations on it, before voltage or power is applied to the capacitor, the voltage across it is 0. Then at t greater than 0, we have a voltage of 100 e raised to power 2 minus 2 20,000 sine 40,000. Now we are required to find the current at t equals 0, the power delivered at t equals pi over 80 milliseconds, and the energy stored in the capacitor at t equals pi over 80 milliseconds. If you're very familiar with the process of differentiating this, you would know that this is we have to use the chain rule here, and let's call this let's call S 100 e raised to power 20,000 t, and let's call R sine 40,000 t, and we know that the V dt will be equals to R ds dt plus S dr dt. Now, what would the value of the S dt be? That would be minus 20,000 multiplied by 100 e raised to power minus 20,000 t. So the S dt would be equals to that would be 2 million. 1, 2, 3, 4, 5, 6. Okay. E raised to power minus 20,000 t. Then the R dt would be 40,000 cos 40,000 t. We differentiated this. With that, we can say that the V dt is equals to this times this, that will be 4 million e raised to power minus 20,000 yeah, t cos 40,000 plus okay, this times yes, this times this. Okay, that will be minus 20, okay, minus 2 million, yeah, 2 million e raised to power minus 20,000 e raised to power t sine 40,000 t. Okay, we can then factorize this, and we would have 2 million 1, 2, 3, 2 million e raised to power 1, 2, 1, 2 t 2 cos 1, 2, 1, 2 t minus sine 1, 2, 1, 2 So this is the value of dv dt. This is the value of dv dt. Now that we know the value of dv dt, we know that the capacitance C is equals to 0.5 times 10 raised to the power minus 6 farads. So we can just multiply them together to find the value of our current. So I would be equals to 0.5 times 10 raised to the power minus 6 times 2 million, 2 million e raised to the power 20,000 t into 2 cos 40,000 t minus sine 40,000 t. Okay, so and that will equal e raised to the power 20,000 t. These two cancel, they're reciprocals of each other. 2 cos 40,000 t minus sine 40,000 t. Now let's not forget that this is I of t. This is I of t, and we're asked to find I naught. So I naught would be equals to e raised to power, this would be 0, or this power exponent will be 0. So e raised to power 0 will be 1 into cos 40,000 times 0, that would be 1. So 2 multiplied by 1 minus this would be 0. So that would be 2 amperes. So I naught is 2 amperes. The next part of the question, where we are asked to estimate the power delivered at this time and the energy stored at this time. I find it very convenient to calculate the voltage at those time voltage at pi over 80 milliseconds. When you calculate that, we can use it to estimate the power P is equals to IV, or the energy stored, which is half CV squared. So let's say V as pi over 80,000, because it's in milliseconds is what we're interested in. So we say 100 e raised to the power minus 2,000 pi over 80,000 multiplied by sine 40,000 over pi over 80,000. I'm writing this here because it is not exactly relevant. We can just put this in our calculator and it will give us the answer straight up. So I'm going to do that right now. We should pay attention to the fact that these angles are in radians. These angles, they are in radians. So if we do substitute t is equals to pi over 80,000 seconds in this equation here, we arrive at v at 80,000 seconds, and pi over 80,000 seconds to be equals to 45.59 volts, and I at the same time would be equals to 0.46 amperes. You can just do that with your calculator, and we can then say that the power delivered at that point in time is 45.59 multiplied by 0.46. and that would be equals to 20 20.79. Sorry, this would be negative 20.79 watts. To find the energy stored in the capacitor at this same time, that is W is equals to half CV squared. So we say 1 over 2 multiplied by 0.5 times 10 raised to the power minus 6. V is 45.59 squared, and that would be equals to 5.19 times 10 raised to the power minus 4 joules. And that is how you solve equation of this format based on capacitors. See you next time. Bye. It's a problem with a very easy solution. We're just going to have to do a little bit of calculus. Okay, now we want to find I at t equals 0. First things first, we know that I across a capacitor is equals to C dV dt. So we have to find I naught. We have to know the value of dV dt. We know that V is equals to 100 e raised to the power minus 2 20,000 T sine 40,000 T. So we need to know what dV dt is to go forward in our calculations.